It would be. It's not clear cut. All right, so TDM, time division multiplexing, versus FDM, frequency division multiplexing. Time division divides up the entire bandwidth. By an amount of time for you to send data signals over it from multiple connections. So the idea of multiplexing is being able to put multiple communication channels over a single data link. Time division divides that up in terms of the amount of time that each of those connections gets to use the entire bandwidth of it. Frequency division divides up the entire bandwidth of it amongst some number of frequencies. In our examples we used, it was among if we had 10 things we were sharing over the cable, it was among 10 frequencies, but there could be kind of a hybrid where, it does a little bit of time division across frequency division multiplexing. So if you have 1,000 communication channels you're sharing over a single link, you may not want to divide the bandwidth up by 1,000. Maybe you want to divide the bandwidth up by 10, and then time division multiplex across frequency division multiplexing for 10. But in any case, frequency division is dividing up the bandwidth among the communication links.
Quick question about that.
Mm-hmm.
With frequency division, does it have to be an even speed across the board, or can you prioritize? Can you give one process 30 to...
Hybrid approaches would allow you to do whatever you want. If it was just strict frequency division, that just divides it up evenly and you go from there. But rarely is that ever the case, especially when you consider in practice you're going to have, the whole concept of multiplexing says today we want to run 10 cables across campus. Well, in a week we might want to add one more. A year and a half from now we add another dorm that needs another data connection, we add another one. So it's one of these things that really needs to be flexible, and sometimes you have to get some more physical hardware to actually do the multiplexing. Sometimes you could just add to the existing hardware. So almost always it's some sort of hybrid approach as opposed to any of the strict ones. Okay, so last time we talked a little bit about delays, what things cause the delay, propagation, transmission, nodal processing, amount of time it takes to queue. So all these things add up to some amount of delay. We talked a little bit, I think it even gives an example on here of a trace route. So here's real internet delays. So this would be an example of a trace route coming back. So we go from here's our local router. Notice it only took like 1 millisecond. So to go, this is UMass EDU. All right, so to get from the computer they were on to their edge router was almost instantaneous, right? But that was still 4 milliseconds of time. Not a whole lot of time, but more than 0. All right. Then they made another jump, still pretty quick. So actually, this is probably an internal router. This was probably an internal router. This is probably when they left, were leaving campus. So 6 milliseconds, 5. Then you start seeing it go up. So we're at 16 milliseconds, 21, 22, 22, 104 milliseconds. All the way down. This took 126 milliseconds. So we start seeing these things add up over time for the delays. Now, from our perspective, 3,000 milliseconds, or let's just say 1,000 milliseconds, is 1 second. Okay? So 110 milliseconds, which on paper there looked like it was a lot, is 1/10 of a second. That's not that much, right? Okay, so if you go back down to this and you start adding these up, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's say that was probably add all that up. Let's say we're at 1.5 seconds, 2 seconds. So all this probably happened within 2 seconds. All this stuff. So human time, that's a lot of stuff that all went down within about 2 seconds. Okay. Okay, so now packet loss This is when bad things happen, when we start having traffic jams, and at the point where data is coming into a communication link, it's not trying to avoid other packets. So we can think of our communication links kind of like an interstate, but the engine's running, but nobody's behind the wheel. Okay, we're not steering around other packets. We're just flying down this communication link using electrical signals, a digital signal, and there's a possibility, depending on where delays are, that we're going to smash into other packets and corrupt them. Similarly, we also have possible data loss that's actually happening at the time of going perhaps from the queue onto the data transmission, onto the link. There could be packet loss there, or data loss there. So when packets get corrupt, they need to be resent, and we'll talk about TCP IP. But the idea of storing and then forwarding those things takes time. And that's where all these delays start adding up. So stuff takes time. It's not just instant. All right, so throughput. The rate at which bits are transferred between sender and receiver. We've been kind of calling this bandwidth. So instantaneous is the rate at a given point in time. Average is the rate over longer periods of time. So this communication channel here, this pipe, has a bandwidth associated with it. The total speed that it is theoretically capable of carrying data. Things that will affect this, things that will affect the actual throughput, the actual transmission time of data will be network congestion, the amount of delays, how busy the hardware is in general. You might not even have a delay at one end, but it can't accept new things coming in for whatever reason. So you have theoretical maximum bandwidth, and then you have realistic input. And this kind of comes down to like our speed tests on our internet connections. So we could run a speed test 5 times in a row and get different numbers, right? So that would be an instantaneous rate given at a point in time based on all the variables that were set up at that exact point in time. Now, if you do 1,000 speed tests per minute for 5 hours, and you take the average across that, that's going to give us more of an idea on what type of communication, what kind of throughput do we have between us and wherever that speed test is being done. You know, on average, what's that look like? And keep in mind that the throughput between us and an endpoint will change for every endpoint. Make sense? Okay, so if we're downloading a file from Apple, well, if you look at it 1 second, you might be getting 2 megabytes per second. You look at it another, you might be getting 4 megabytes per second. You might look at another, you're getting 240K per second. Something like that. But maybe Apple can deliver stuff to you consistently at, an average at 3 megabytes per second, let's say. That might be a speed that you're not even capable of getting from another server because their upload isn't fast enough to even give you that. Make sense? Okay, so throughput is a measure of speed between sender and receiver, not a measure of bandwidth on an individual communication channel. On the medium, the wire. This is a little creepy. The server sends bits or fluid into the what fluid is the server putting into the pipe? Pipes that can carry fluid at I think they're making kind of a plumbing example here, but they never actually say plumbing example. Because they still say server. And it's going, you don't want to dump fluid into this computer. I don't think it matters what kind of fluid it is. Okay, so. All right, not important, not important. Okay, this is what I was kind of talking about before. A bottleneck link is you might have a piece of equipment on the end that doesn't technically have a delay. It just isn't taking stuff in as quickly as you're able to deliver it. Make sense? It's not that it's too busy. It's that stuff is traveling along the communication link faster than you're able to take it off of the communication link. All right, so maybe the analogy might be if you turn a hose on full blast and the water's firing out of this communication link, but the idea is, let's say that the hose is you have it pointed at your computer. Okay. Well, we're going to put some real danger into this. So you've taken the hose, you tell your friend, you give them the thumbs up, you say go.
That's the fluid.
The fluid, okay? This isn't water. It's generic fluid is what we're working with here. So that's actually an important part of this discussion. That it's generic fluid, not water. All right, so you're holding it there. It would be bad if any of the generic fluid gets on the computer. Okay, you've decided the best way to deal with this is that there's a sink over there. And any fluid that comes out of the hose, you want to make sure gets over to the sink. And you've decided the best instrument for getting it over there is going to be a teaspoon. Okay, now remember, your friend is turning the generic fluid source on high. I don't know where we're going with this.
Just going to add that.
We got the generic fluid source and a teaspoon. This can't be okay. So, anyways, so you have a teaspoon and you're going to be trying to take some fluid over there into the sink. Come back, fluid into the sink. Meanwhile, is the hose likely going to be putting more fluid out than you can get to the sink via teaspoon? So there's likely we're going to have problems, right? So in that example, okay, we might be a router. This is the router. Well, no, that's the router. That's the router. That's the actual router. We're the communication link that takes the stuff off of the data link into the router. We're that part. And the data is coming in at 100 miles an hour, and we're able to take it in at 1 mile per hour. All right? So it's not that there's a delay on our end. We are just only so quick. All right? So at that point, you might have data loss because the water is going to be flying out, fluid, sorry. So generic fluid is just going to be coming out, and we're not able to deal with all of it. So there's going to be loss, data loss. That's going to have to get resent from the... It will be fluid loss. You'll have severe fluid loss. Okay, so any data that was lost because of that then needs to be resent in whatever way makes sense. We haven't really discussed the various ways things can be resent, but we can understand that would be an example of data loss, and that would be an example of a bottleneck. Okay, too much data is coming in at a certain point, and we can't deal with it. Okay. This actually looks like a pool of fluid. Okay. No,
generic.
That's not important. Right there. Okay, protocol layers, good. All right, so here's the various layers of a network. And we've already talked about some of these things. We've just used them as just terms that we're supposed to know what they mean at this point, but we haven't actually discussed them. So, our networks are made of a whole bunch of different pieces. We have hosts, we have routers, links of various media. So we could have fiber optic cable, we can have copper cable. Those would be like Ethernet cables, coaxial cables, that kind of stuff. You actually have applications. So this is software that establishes communication links, establishes network connections. You have protocols, which are languages. So as our stuff is traveling across communication links, they are communicating between a sender and a receiver using some sort of protocol. Then they decided just to put generic hardware and software in there as our catch-all, I guess. So the idea here is there's a whole bunch of different players in that make up a network. And then we think about something as big as the internet, which is a network of networks of networks of networks. Just keep going with that at least 30 or 40 more times probably. So really complex thing that has a whole bunch of each of these things, including the catch-all hardware and software that might be connected to the networks. That could be toasters, fridges, other network connected things now. Okay, so is there any hope of organizing a structure for networks like this? So can we come up with some sort of model for how we can build our networks in terms of these things? And we're going to see that there are common pieces as part of networks, and then some of this stuff becomes extraneous that have nothing to do with the central core of the network. Okay, so if you go into your car and you put let's say you put something on your, like a garage door opener on your visor. Okay, it's going to stay on the visor, right? The back of the garage door opener thing is the little metal hook thing that you push on there and it squeezes onto the visor and it stays, right? Does that staying there have anything to do with the fact that your engine is able to run and all the things that go in there?
Depends how good your car is.
Probably not, right? Okay, so think of that as being a network. I mean, your car is a connection of a whole bunch of different things that have to work together in a certain way in order for it to go, right? Okay, and your garage door opener on the visor has really has nothing to do with whether or not your car runs, correct? Now, there might be some other things. For instance, the ignition. Does that have to do with whether or not your car runs? Well, it does from the perspective of it initially turns the car on. I had a friend once who had an ignition and the ignition would just fall out. So they would have, when they got in their car, they would pick it up off the floor, and it was just like just a metal cylinder thing. They would put it back in and turn it and work just fine. Okay? But so one might say that their ignition was broken. Certainly not factory installed. Okay? But it's still, once they started the car, it was fine. Make sense? So that had something to do with the total workings of the car, but everything doesn't have to do with everything else. Once data has left a router, once it's out there on the internet and doing something, that router is no longer important from the perspective of that data. Make sense? Okay, so if we try to understand networks in terms of all their complexity, we can't. There probably is some sort of statistical thing we can do that says that technically it is not an infinite complexity, but because there's only so much electricity that can power as many things. But the idea is that certainly there is a lot of complexity that we can just keep adding to a network, and not everybody can understand it, right? If you get a job as an IT professional working at a university or an enterprise type place, it might take you 3 months to learn just how the network in the building there works. All the different pieces of equipment and how the things that plug into the different switches, all that stuff comes together. What does this server do? What does this server do? What does this server do? That's you in one building or one collection of buildings. How much more complex do you think it is? Like, let's take downtown Chicago. How long would it take you to learn about how all the networks function together in all the office buildings in downtown Chicago?
How many lives do you have?
One city, probably about 10 city blocks, and zillions of hours of learning where documentation is going to be suspect. I mean, that's actually a big problem in technology today, is where's a lot of our documentation stored? We wish it was stored virtually in the cloud. Where's it actually stored? We even hope it was in a paper copy.
Somebody's brain.
Somebody's brain. Okay? Probably some old guy who's retiring in 6 months, and they just hired somebody who was the best we could hire at the cost, who, while he's being trained, already has his resume floating around for his next gig. And this guy has to somehow get his knowledge transferred from his brain into this other person who might leave in 5 minutes. Okay? It's actually created an entire industry. It's pretty common for people who are retired to then continue to be consultants, even for the company they retired from, because they're the only one who knows how stuff worked.
Protecting their assets.
Well, you could look at his job security, I suppose. But, in any case, networks are very, very complex, and if we try to understand networks of any sort of large size in its details, things get lost quick. So we have to break them down into baby steps. Okay. So we could certainly see a little example here where they're talking about air travel. There's all sorts of things that have to happen in order for you to get from point A to point B, and you don't have to understand all those individual pieces. You may be aware of some of them. You might be unaware of other ones that you didn't have to use, that kind of stuff. All right, not important. Okay, so why layering? Dealing with complex system. Explicit structure allows identification relationship of complex system pieces. We're going to look, I assume they're going to tell us about an internet layer. Yeah, transport, okay. So the idea is that if we can give kind of high-level descriptions of the various layers in a network, we can then say this application, this tool belongs in this layer. Now so to kind of take layers, to give it a little bit better meaning to us, think about a church. We'll get the Christian worldview point here. Okay, so I go to Beautiful Savior Lutheran Church here in Mequon. By the way, did you guys get my email? Extra credit opportunity. It's actually a really cool event. We had it last year there. Several Concordia faculty, Nathan Jastrom, Reverend Dr. Nathan Jastrom, is one of the guys, and he's really smart. Knows a lot about theology stuff, and so it's kind of a cool opportunity. Well, first you get free food. That's one bonus. But on top of that, it's called Theologians in the Hot Seat, where you can just ask them kind of, let's say, tough theological questions. Like I was talking to a student earlier who's coming, and he was mentioning, I guess I'm giving away a question, but talking about gay marriage and how the Lutheran perspective on it. You know, some of these topics that are very hard topics to discuss, trying to listen to these theologians give arguments from a biblical standpoint. So, you know, things that wouldn't usually come up in a Bible study because nobody's going to be qualified to answer it, type thing. So it's, you know, it's usually an interesting type thing. Another good one, if you want to get you know, outside of that realm, might be like women in ministry. That's one I think they talked quite a bit about last year. You know, female pastors versus non-female pastors, and what's allowed, what's not allowed, and that kind of stuff. So cool event, and I'll give you free quiz grades. If you show up to just the event, you get one free quiz. If you also come to the church service before it, which starts at 9, I'll give you a bonus quiz. But you can't just come to the church service and leave. You don't get any quizzes for that. You have to come to the free food and the presentation thing to get any quiz credit. You get a bonus quiz if you also come for church. I'm not bribing you to go to church. I'm giving you a bonus if you come to church. Okay, so the idea there, what I was getting at is, so Beautiful Savior is a relatively small church. Our Sunday service maybe has 100 people, 120 people, so we're not one of these giant, huge super churches. So we would say that we're a relatively low complexity network, okay? Well, even at this church, though, we have several committees. We have a stewardship committee. We have a evangelism committee. We have we have a general board. We have a committee of elders. So each of these committees has a role to play in the church. Okay. So, for instance, I'm on our stewardship committee, and we don't know what we're supposed to do, but we know what we're not supposed to do. We don't mess with the stuff that this committee talks about, and this committee talks about, and this committee talks about. Instead, whatever else falls out of the nooks and crannies goes into our lap, and we say, okay, this is now under our purview. So we deal with that stuff. Okay, so we have 4 or 5 or 6 different committees, and all of these committees working together solve all the church's problems. Okay, we have a comfort dog, just like Concordia does, and so we have a committee specifically for dog-related activities. So we literally have 5 humans who meet to discuss what the dog does. I find that very entertaining. Okay, but the idea is that if you had one person, or even a group of people, let's say you had 5 people who had to handle everything that happens at even a small church like that, a lot of things would go wrong, right? There's too much stuff, you know, and then you have people who have all sorts of different interests. You know, we have an organ committee. The organ committee is interested in music stuff. Well, what if you don't like music? Well, I don't like music. They probably don't want me on the organ committee because my vote's always going to be get rid of the organ. right? Last year we spent, I don't know, like $75,000 on a new organ. They're expensive. That was the cheap one. We went with the cheap one, 75 grand. There's a lot you could do with 75 grand. But you know what? I found out that music's really important to a lot of people. They were able to raise additional money without taking it from someplace else to pay for this organ. Okay, so you kind of need different people to be on these different committees in order to solve any problem. So we might call those the layers of the church. Okay, each of these does a job, and the problems of the church, the data associated with the church flows through these layers, and in the end, you have something you might call a functional church, as far as churches function. As if you are a churchgoer, have been associated with things like churches in the past, you usually what you get on the other end is something that you might say that was an acceptable product, but not as planned. They spend 6 months planning something, and then what happens in the end, you're like, oh, that went well. It didn't go like we thought it was going to go, but it went well. And that's typically considered to be acceptable. So in any case, that's kind of a layering approach. So networks do the same thing. Some textbooks, I know I gave you guys, I haven't read the book, so who knows what's in there, but your book is either going to have a TCP/IP 5-layer model, or it's going to have the OSI 7-layer model. They're the same layers, all they did is combine a couple layers together. Same crap. So whatever this slide set talks about is perfectly acceptable. Okay, so this one's talking about TCP/IP. So we have an application layer, a transport layer, the network layer, the link layer, and the physical layer. Okay, and we've really talked about these already, just not by name. So physical layer, we're just going to do this at the, they even say them over here. So I was just going to tell you. So physical layer is the bits on the wire. So this is the actual copper cable or the fiber optic cable. Okay, the link, data transfer between neighbors, neighboring network elements. So the link, this is that queuing thing where, the queuing would occur in the link layer. That is the guy who is bridging between the network in here and the physical layer out here, and is in charge of getting data onto this physical medium, and vice versa. Stuff comes off the physical medium, comes through this link layer to get into the internal network. Okay? Network, routing of datagrams from source to destination. So this would be like our routers. Right? So if this is the router and this is the physical cable, the link layer is the stuff that happens between the inputs and outputs on the router and that physical wire. Okay? So we might think of it as the little thing you plug the Ethernet cable into. It has little flashy lights on it, but inside there's some complexity to what it's doing. There's some software that runs that. There's some hardware that runs that, and that kind of stuff. All that crap is happening on the link layer. All right, transport layer, process data transfer. Huh? It's like the Little Caesars commercial. Pizza, pizza. Process. Okay, well, that's stupid. So in any case, the transport layer here is a lot like the link layer here. Link layer here we can think of as being mostly physical. The transport layer here is what we can think of as being mostly software. Okay, so you have your applications. So supporting network applications, which by today's definition is pretty much all of our applications. It's pretty uncommon now for us to have an application running on our computer that isn't network aware. Even on a Mac, TextEdit uses iCloud now. So it's very difficult to find a program anymore that doesn't do something with the network, with the internet. Okay? But specifically, we're talking about network-aware applications here. So you have network-aware applications here, and when you hit save on TextEdit, and it needs to get that file somewhere up on iCloud, which is out there in the abyss somewhere, okay? It's going to go through, more than likely, software at the transport layer, which is going to take your data and turn it into packets, a couple different kinds of packets. They talk about UDP and TCP packets here. We'll talk about the difference. But our top level example might be here that UDP is what video streaming would have in it. TCP would be pretty much everything else. You might say, if you were really giving definitions, I'm sure I'll give it again, but TCP means you definitely don't want data loss. UDP means some data loss is acceptable. And you might say, well, when is data loss ever acceptable? Well, if you're in the middle of watching a YouTube video, or you're watching a movie streaming from Netflix, and that thing's playing at 40 frames a second, if one bit of one frame is corrupt, do you want to pause your movie and have them resend that entire frame so you can see that for 1/60th of a second? Your brain's probably going to fill in the gaps. You won't even notice, right? When we start noticing is when there's major data loss and it gets all pixelated and stuff like that. But generally speaking, streaming video, if we lose a bit or two here and there, we're not going to notice. Or at the very least, even if we did notice, we'd rather the video keep rolling than have to pause to resend something that we don't really care about. Okay? So UDP kind of plays into that type of thing. It's also used a lot in gaming protocols. A lot of times what you're doing in games is very much streaming data. When you're playing a game that uses the keyboard or even the mouse, it doesn't matter, and you're holding down the up arrow to run forward, or you're holding down both mouse buttons to run forward, that's sending a stream of instructions, one after another, saying keep running, keep running, keep running, keep running, keep running. And if one of those keep runnings doesn't get through, you don't want it to resend it. Because if it gets resent, now stuff shows up out of order, and then what happens? You stop running, and all of a sudden your guy starts running. Because it took 7 tries for it to resend the start running packet that you stopped running a while ago. So, and we'll see more examples of that. In any case, transport layer is typically a piece of software that sits between your network-aware applications and your network hardware and your internal network. That takes your data from your application, turns it into what's usually called a marshallable format. That's a hard word to say, marshallable. Try it. Marshall. We're marshalling data. We are marshalling data. Yeah. So what we're doing is we're marshalling data. Marshalling data means sending data, but it's just a much more fun way of saying it. So in order to marshal data, we must turn it into a marshallable format.
Yeah.
I can't say it one time slow.
I think we need a competition.
All right. So in any case, that transport layer is going to be the software that's going to take whatever our application says, and it's going to turn it into the right kinds of packets. That's probably the easiest example for right now, since most of what we're going to be talking about in here is packet switch networks. For those of you who had the operating systems class, when we talked about some of the different ways of doing memory management and stuff like that, in the end, what did we talk about? We talked about paging memory. That was the winner. Okay, that was what your memory managers do today, is paging memory. Period. I don't care who the competitors were before, that's what they do today. Our networks today are packet switch networks. We had all sorts of competition in the past. We had token ring networks. We had something called ArcNet. ArcNet was cool. We'll talk, I assume this slide said it'll talk about them. If not, I'm sure I'll get off on a tangent. It's going to be really funny when my mind finally goes and all this stuff isn't in there anymore. I just sit here with a blank look. I'll probably be twitching more than I am now. Okay. Then I might have to bring my own jar of generic fluid.
For what?
Huh?
For
I got to do something to entertain the class. Right now I have data flow. I have to have some sort of flow then.
Well, at that point, you might have to pen other generic fluid.
Oy. All right. So in any case, most of our networks today are packet switch networks, where we divide up our data into tiny little packets. Why? So we have less data to resend. And when we talk about TCP/IP in more detail, we'll be talking about some of those decisions we had to make between how big should that packet be so that it's the right size, so that when we have to resend a packet, we're being as efficient as reasonably possible. Make sense? So a lot of these things have kind of interesting answers, and we'll kind of talk about how it evolved. Because we might just say, well, why not? And this is the same example we had when we talked about memory management in the operating systems class. When we talked about paging memory management, we talked about the frame size. And that was during the whole conversation about internal versus external fragmentation. Right? Internal fragmentation is the amount of wasted space within a page of memory. Well, if we decide that internal fragmentation is bad, what do? We'll just make your page size 1 bit. You're going to store anything, it's going to be at least 1 bit. Well, great. But now you're going to spend so much time switching from page frame to page frame to page frame, and then having to swap things into real memory from virtual memory, that now your machine is super slow because you didn't make your page sizes big enough to actually accomplish anything. All because you wanted to save a little bit of internal fragmentation. Kind of make sense? Same thing's true here. We can make our packets 1 bit big and have 1 trillion of them to send for an email message. Or we can make our packets somewhat larger than that, knowing that in the case of an emergency, we will lose more data at a time, but resending that data isn't that big of a deal. Okay? So in any case, that's what the transport layer is doing. Application, transport, network, link, physical. Oh, see, I told you.
That's the
7-layer one. Both of them are in here. At least I wasn't lying. And I was guessing too. I knew one was 5 and one was 7. All right, so OSI level, or OSI 7-layer model, still has the application. Then it has presentation, session, transport, network, link, and physical. And you're going to see that these guys are all the same as what we had before. We've added 2 additional levels, presentation. This allows applications to interpret the meaning of data, encryption and compression, machine-specific conventions, blah, blah, blah. So this, along with session, does the exact same thing as transport did here. They just split it into 2 layers. Does that make sense? It doesn't matter is the punchline. Now remember, the whole reason we're doing this layer thing is to break our network complexity into smaller pieces that we can work with. Realistically speaking, from a developer perspective, if we're having to do both of these things, allow applications to interpret the meaning of data, blah, 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 then synchronization, recovery of data exchange, blah, blah, all the stuff that the transport layer used to do, to split it into 2 layers like this, to me almost seems like a waste. Neither of these layers does enough for it to be its own layer. Because we now, especially today, we have our own standards for handling that kind of stuff. Because everything's packet switched now, and we have standardized compression techniques and that kind of stuff. Okay, doesn't matter how you want to think about it, but we've broken our networks down into individual pieces. Okay, so we see that here's our source and destination, and notice as something is leaving our application, let's say you're doing email. So this would be our email application up here. The email, when you hit send, the magic is going to happen at the application level, which gets sent to the transport, which gets sent to your network hardware. At that point, it's left your computer. Okay, it's flying out over Concordia's network. It hits the link on the, eventually it hit the link on the edge router. Okay, actually we're still here. We're still on campus here. So this is still on your computer. So leaves your email client, hits the transport layer, goes onto your network interface card, your Ethernet card or your wireless card in your computer, gets to the link, which is either where your Ethernet cable's plugged in or where the flashing lights are for your wireless that shoots it out into air. Okay, that's the link. Then we're out to the physical layer. At that point, it's either on the Ethernet cable or it's floating through the air. Okay, so in this room, I am looking at the physical layer of a network right now. It's just out there. There's radio signals and, you know, whatever. So that's all leaving just our computer. So the TCP/IP, this is usually called the TCP/IP stack. So all these layers that exist here combined is the TCP/IP stack. All right. So now it's left the computer. It's flying through the. So let's just use the wired example. So we're at wired example. It's going to get to a switch. Okay, a switch is what's used to connect multiple networks together. So it's going to get to this switch. The switch, notice it's going to hit the link and the physical, but it doesn't go up to network transporter application. It's not that it's not that those three layers couldn't exist here, because there are some switches that are called managed switches that do have some application layer stuff on them. They have software that the switch itself runs. It runs an operating system. So at that point, the switch is kind of like a computer. For those of you who have like a Linksys wireless router or something like that at your house, when you set it up, you probably plugged it into your network in the house, and then you remote it into it through a web browser. Typed in 192.168.1.1 or 10.0.0.1 and gave you the login, admin, whatever. So it's running a little web server on it that has the thing that you can mess with software and that kind of stuff. So that router, or there's also managed switches that would work very similarly, they have more of these layers represented. Okay? But for an unmanaged switch, we're going to come off our Ethernet cable. We're going to hit the physical network of the switch, and then we're back out. Well, actually, you see it did both. It came off the physical network here, went into the link, came out of the link, down to the physical. So it just jumped back onto another wire here, like train tracks. It left this line and got onto this line. Heads into our router, another piece of equipment. From the router, it hits the physical, then the link, then the network layer, then rides it right back down. So comes in off the stack, or comes in off the link, rides up the stack, comes over. Now it's leaving that router after it's done its whatever magic in the middle of this network layer. That's the physical stuff the router does. Then it's going to come down and it's ultimately going to arrive at this destination computer where it leaves the physical wire, hits the Ethernet network card. It's in the network layer. Now it's getting converted back into something that the end application will understand. So this is where the data is now marshaled back to, or I guess demarshalled. No, marshaled. I've misrepresented marshaled. We serialize data and then we marshal it back into a whole. So data is serialized, that's when we chop it up into packets, and we send it over a network in a serialized format. When it arrives at the other end, we marshal it back into a whole. 99.25% certain that's right. Okay, so notice at each of these individual links, we had some or all of the 5-layer implemented. And it wasn't that these 5 layers couldn't have been implemented over here. It was all because this computer, the switch, which is a computer, is a much more domain-specific type of computer than this guy here. So they only chose to implement the parts of the layers that made sense for this guy. Got it? All right. I'll see everybody on Monday. We might have another quiz about TCP/IP or possibly human centipede.